Don't worry, we don't need to start bang on. That's fine. Sophia, welcome to the Astro podcast. How are you doing today?
I'm doing great. Thank you for having me.
It's a real honour, and I can tell from your Twitter that you seem extremely busy. So thank you for squeezing me in. I thought we'd start with a very easy question. What is the universe even, and how did it come to be what it is today? If a child asks you, how big is the universe? What is the universe? What would you say? What does it mean to you? What's your sort of explanation of it?
Okay, so that's a really kind of loaded question. The way I guess that I would explain it is that the universe is everything that we can ever contact or ever understand. So it's everything that exists to us. The way that it came to be was there was in the very early universe out of kind of we don't really know exactly how it happened or why. So the why is a very difficult question. But we know that the universe came to be in a Big Bang. Now, the Big Bang isn't really an explosion. All it is essentially just everything starting and kind of like expanding. Okay? And so everything started at a really dense and hot state where everything was kind of sort of smushed together and very hot, and all particles were bouncing off each other. And then suddenly, as the universe expanded, eventually things cooled down and were able to start to come together and coalesce and form into the stars and the galaxies that we see today. And one of those galaxies, which is like a collection of stars that's held together by this stuff called gravity, the same stuff that holds you down on the ground or pulls things down, like if you were to drop a ball and it drops to the ground, held together by gravity. And we live in one of those called the Milky Way. One in one of those, or around one of those stars, the sun, on this lovely planet that we call Earth.
So we're in the Milky Way. I know that much. If you're lucky enough to live somewhere, I don't know, on the equator, in the middle of nowhere, where you can see the Milky Way, are you seeing one side of it? Like how, are we right in the middle? Are we on the outskirts? When you're seeing the Milky Way from Earth, what are you seeing? What are we seeing one side of it, or how does that work?
Yeah, so we're kind of the Milky Way is a disk galaxy, so think of like say think of a CD. It doesn't move in the same way as a sort of, or let's say a DVD disc. I know that those are kind of obsolete nowadays, but let's just say, okay, I'll use a coaster. It looks kind of like this, except it's got like a bulge in the center. So and it's and all that entire disc is like full of stars. We live right around here. Okay? So we live right around here. And so when you look into the sky, depending on what time of the year it is, sometimes we can actually see the bulge. Sometimes we can look into the center and see the bulge. And so what you essentially usually see is a band across the sky. So you're seeing one of the spiral arms of the Milky Way. So our Milky Way is a spiral galaxy. So it's a disk, but it's like so there's a bulge here, and then there are like spiral arms coming out this way. So we're looking at one of the spiral arms streaking across our sky. Depending on what point, I guess what point in the orbit around the sun we are, like so where we're facing, we can sometimes see that bulge, and sometimes we see the edge. But all the time, when you ever see that streak, you're actually looking at one of the arms of your galaxy.
That's so cool. And how significant is the James Webb telescope? Because am I right in thinking that will allow us to see the universe in its very early stages, and will shed some light on how the universe was formed?
Yeah, so the James Webb is really a state-of-the-art telescope. It's the first of its kind. There's so many lovely things or amazing things about it. Like it's the first essential origami type spacecraft that we sent into space that unfolded in space, and it's got a really beautiful sort of hexagonal type mirror shape, and it is going to look. So it's looking at this specific type of light called infrared. So it's a type of light that we can't see with our so we can't see it with our eyes, but the infrared light is special because it can pierce through things like dust. And so, so that's one thing. So it will be able to look through like nebulas are kind of like full of gas and dust and all that stuff, and so you'd be able to like pierce through that, which is great for also exoplanets because exoplanets are covered in like clouds and things like that. But also because infrared light is also like a longer wavelength, the universe is expanding. And so, and it's expanding at an accelerating rate. As time progresses, it expands, so it stretches apart faster and faster with time. And so light that is emitted in the universe is also stretching. So the further away that an object is, its light has been stretched even more. So the distant parts of the universe that we're trying to reach have already stretched beyond that visible wavelength. And so we're hoping to be able to peer back as far back as like when the universe was 100 million years old. So we'll be looking at the very, very first stars and the very first galaxies. I'm really excited about this telescope.
That's so awesome. I'm aware that I've just sort of jumped from like the Milky Way to the James Webb telescope, just sort of asking stuff that I'm kind of aware of but don't really understand the significance of. So you're clearly passionate about the universe and the cosmos. Tell me a bit about where you are at the moment, because are you still a PhD candidate? You're still working towards your PhD in cosmology?
Yep, that's right. So I'm at the University of California in Irvine. I'm in my 5th year of my PhD in cosmology and astroparticle physics, and I focus on this really weird stuff called dark matter. Which is essentially it's stuff that's just like us. So we're made up of particles, but we also have our particles interact in different ways. We have like an electromagnetic force, which is why we could see, and all these so strong force and stuff like that. These forces are the reason why why particles come together to form objects like my phone and your phone and things like that. Whereas, so imagine that you could take that apart into its most constituent particles. Dark matter would be similar to that, except it doesn't interact with the same forces, so it can't come together to form atoms that form molecules that then form your phone. So it just kind of sits scattered around the galaxy and is invisible to us. We can't see it and we can't touch it. And it's actually 6 times more abundant than the stuff that we're used to.
It's so crazy to me. I've sort of watched various shows and been to conferences with people talking about dark matter, and I still can't quite get my head around it. And he talking about sort of self-interacting dark matter, which I know is a focus of yours. I still can't really understand what it is. So how does it interact with itself? I don't really get the how that works.
So it's I guess the first thing that I should say is that we don't know what dark matter is. Like, we don't know what it is yet. We know that it exists because of the way that it interacts with gravity. So we're lucky that it interacts with gravity as well as us. So so we can tell that it exists by, for example, the way the effect that gravity has on stars. They're moving too fast in galaxies, for example. We also see it encoded in this thing that's like a very baby, like an early picture of the universe, like when the universe was a baby. We call it the cosmic microwave background. So it's kind of like it's embedded in that information. We know that dark matter is there, but we don't really know what it is yet. We haven't actually detected the particle in the same way that we've detected the stuff that we're made of. So we kind of try to use different like models. The most standard model, or the most commonly used model, is one that says that dark matter particles don't interact with themselves or anything at all. So it's like if you were to take 2 billiard balls and launch them towards each other, imagine them just passing through each other like the other didn't exist. So that's what the standard model of, or the standard, I guess, more common model is what I want to say for dark matter assumes, is that dark matter particles don't interact at all. And every interaction that exists has to have some sort of force to mediate it. So that would just mean that that it doesn't have a force to interact with. So the type of dark matter that I study says that, well, maybe there is a force that interacts with, and so that you can then picture 2 billiard balls, and just like you would imagine that they would actually scatter off of each other. And that force would be like a dark force of nature that we haven't discovered yet.
It's so crazy. So you study it, but you don't know if it's real. So is it all theoretical and modelling and making various assumptions about the framework of the universe?
Okay, so It's not that we don't know it's real. We do know that it's there.
Hmm.
There are so some people who are listening to this might have heard about like ideas where, perhaps we don't understand gravity well, and it's just sort of manifesting itself in that way, which is why we see stars moving too fast in galaxies. The way that things, like, the speed at which things move is all due to the force of gravity. And so some and so because stars are moving too fast, it's kind of proportional to that. So like the more gravity that you have, the faster things will move. It's kind of like in the solar system, the way that our planets move around the sun. Um, the closer that a planet is, it actually moves faster around the sun than so like Mercury is moving faster than Venus, and Venus is moving faster than us, and so on and so forth. And we expect that in galaxies too, but we actually see that stars, no matter how far away they are, they're actually moving at relatively the same speeds. So that's with all the stuff that we could see, there's just not enough gravity to be able to provide that kind of I guess that speed that we're seeing, and so galaxies should essentially fly apart unless there's dark matter that's actually giving, adding extra gravity, where some people think that we just don't understand we don't understand gravity. But as I said, like, that's not our only piece of evidence. It's actually encoded in the baby picture of the universe that we call the cosmic microwave background. So you can't get away from that. Like, even if it's entirely possible that our picture of gravity is not complete, but even if it's not complete, we still need dark matter. That's just how it is. So we do know it's there, but we don't know what it is. And the thing that we need to try to figure out then is like, is its property. So how it behaves, kind of like, if it's a particle, then, what kind of forces it will interact with. And perhaps somehow we can then detect it if it happens to, in some weird way, end up interacting with the particles that we detect. So like, we know it's there, it's just that we just don't really know quite what it is yet.
No, sure. It's so interesting. So what's the hope for your niche? I'd call it a niche, but what's the hope for the investigation to dark matter? Like, what will it say? We understand it. I mean, obviously there's the sort of human desire to understand the universe and know the right questions to ask, but is there what are you trying to achieve? Like, it's not just an academic pursuit. I imagine there's sort of a higher calling. What are you hoping to get in terms of answers?
I guess maybe in somewhere in there, you also kind of want to know if there's anything practical or any practical advances that can come out of it. Okay, so with every discovery that we've made in the past, we might not have known like what it was going to bring about. But one thing that we do know about dark matter is that, so there's a periodic table of elements in chemistry. Particle physics has the standard model of particle physics. That standard model doesn't predict dark matter. So if we detect it, we already know that our particle physics model is wrong and we have to rewrite things. And so if we do detect it and learn more about what its properties are, then it would tell us things that that change our view of physics. And so with those changes, I don't know what that will bring, but it could bring many things. Like, I mean, there was a point where light wasn't really a thing, like light bulbs weren't a thing. And so, and then once, you just don't really know. And so I guess, yes, it's the curiosity too, but it's also finding new physics will bring us new technology and new advances, hands down. What they are, can't really tell you, but that's kind of the pursuit is new physics, I would say.
And you're really at the sort of front edge of that. So what is the University of California like? Like, do you find much time to, I mean, I'm being stereotypical, but like go to the beach, live that sort of Californian, preconceived, laid back life? Do you do much of that, or is it very sort of work focused?
So, I mean, I can't really speak to the others. I guess the University of California in Irvine, I mean, all of them will have some sort of, I guess, California type, the ones that are at least close to the coast. You can, we're very close to a very beautiful beach called Laguna Beach. And of course, there's even closer to us. We got beaches that are within driving distance. I haven't been able to do a lot, unfortunately. There's so many things to do around here, like, there's even whale watching, which I haven't gotten to do because I'm always sort of, I guess, busy either working or doing science communication, which I'm very happy to do. And so, but I do want to explore that more. Like, it is definitely available. I feel like a lot of us don't use that as much as we should. But yeah, that's kind of, I guess, in a nutshell. It's
No,
there, but
I completely understand. So you mentioned science communication. I'd love to talk to you about that because that's how I sort of first heard about you, was on your one of your Astro party girl accounts. I'll share the details of. And I read on your, I think it was your Twitter, you were sort of posting a fact that 100 trillion neutrinos pass through each second that you read this. So, yeah. I mean, again, another layman's term question: what is a neutrino? But also, like, how powerful is that on social media? Kind of telling everyone facts they might not be aware of, and sort of information like that you're not going to get sort of in day-to-day life. It's really kind of out there, and you either scroll past it or you think, what is a neutrino? Because it sounds 100 trillion of anything is quite a lot.
Right. So a neutrino is, again, it's another subatomic particle. So it is formed in reactions that, for example, in the sun. So when things are fused, it's really a kind of like they come out of decays. So like weak interactions, that's what we call weak interactions. So when you fuse things together, and there are byproducts, so you'll have like a photon that comes out, which is why the sun is, glows bright. But also with that, you'll have neutrinos coming out. And they're these like ghostly particles that seem to interact with nothing at all. Like you can take an entire light year. So a light year is the distance that it takes, or that the distance that light will travel in a year. And light is the fastest moving object. You can't move faster than light. And so that's about I think it's 9 trillion kilometers. So it's quite a distance. That's a light year. And so if you were to take a light year of lead, so lead, like and it would just pass right through it. They are, and because the sun, because they're created in reactions in the sun and other, explosive events like supernovae, they are constantly bombarding us because the sun is right next to us. And so and that's why you have trillions of neutrinos passing through you, hundreds of trillions of neutrinos passing through you every second. And they are actually another thing that tell us that our model or our understanding of physics is wrong, because the standard model predicts one neutrino, whereas neutrinos actually, they come in 3 flavors. So as they move along, on their path, they'll kind of switch over to another flavor, and then switch over to another flavor again, and that's what gives them slight mass. And so that essentially tells us that the standard model is wrong. So neutrinos are very special.
so on social media, I don't know, kids would see that, and they'll either be drawn to it because they're curious about science, or they might be kind of impressed with the I don't know how to describe it. I guess it's an effect of science communication. It's it's sort of impressive, to know sort of facts like that. So do you find science communication is a good way to inspire, people to of all backgrounds to study STEM and to be drawn into the field?
Yeah, so that was actually the second question that you had asked, and this is really why I do this. As you said, it's not something that you come across every day, like a fact like that. But I feel like there's this idea that the sciences and physics is really hard and stuff, and so when I go and do science communication, I want to share with people the magnificent things that are what physics is and what the universe is, to encourage them perhaps to either take an interest in it academically, or just at least even in just their personal lives to know or want to know about it, because it's all around us and it's so accessible to you. All you need to do, the universe, all you need to do is look up at the sky, and that's it. and it's just right there. It's just available for you at any time. So it doesn't, you don't have to be in the field, but you should definitely like revel in it because it's all over. And this is why I love to do science communication, is to share that with people and sometimes blow their minds.
Absolutely. I think that's a great way of connecting with people and inspiring them to look up at the stars. Another great way that I know you've been involved in is consulting with film and TV companies. You've worked with TV shows like The 12 Monkeys to advise on the science of the show. So how close does TV get to science as we understand it? And because the only example I know of this is, in my opinion, one of the best films of all time, which is Interstellar. And obviously that was, I don't even know who directed Interstellar. James Cameron, maybe. Christopher Nolan. And he worked with Caltech professor Kip Thorne to make sure that the science was as realistic as possible when depicting things like black holes. So how important is that as a way of inspiring people to be drawn into science? And what was your experience like of working with 12 Monkeys, which is another great show?
Yeah. So I think it varies from I guess TV show or movie to TV show or movie, depending on what sort of, I guess, niche it is and what it's trying to accomplish. You'll often find that there's some sort of thing or type of science that's going to be bent. We want to be able to bend it in ways that aren't outrageous, right? And so that was kind of what the sort of, I guess, part of why I was on the 12 Monkeys. I did the fourth season, and it wasn't. So I did like my purpose was a specific thing. Like there's this. I don't want to give too many spoilers, but there's this want of this group, like they want to essentially take time out of the equation, so that time is not a factor anymore. And we wanted to be able to do that. The writer wanted to be able to do that realistically, and one of the ways that you can do that is by using this thing called the Hartle-Hawking state. It was theorized by Stephen Hawking and James Hartle. It's not really too important like what the details are, but it does require that we live in a universe that is different from the kind that we live in, but it's actually something that if we did live in that kind of a universe, then it would make sense, because if you were to take time back, then if you were to like reverse it back in time, then actually space and time split. And so time is essentially taken out of the equation. There's a whole bunch of other stuff that I actually didn't do science advising on there. And so, with time travel, it's based on time travel. And so, it gets very twisted and whatnot, but I think you can't really avoid that when you're doing something that's supposed to be exciting. And so I think once you get into time travel, things can get murky, but it's all about trying to, or wanting to, I guess, or being able to separate your sort of, I guess, need for accuracy and just sort of trying to like enjoy what you're watching. And so like things like Star Wars, for example, there's no such thing as hyperspace. Like,
don't tell me that. I want to think it's all possible at some point.
Well, so in Star Wars, there's this dimension beyond. So I guess where like this hyperspace dimension where you can travel faster than light. That exists, we do not know, but we know that there's no way to travel faster than light. One of the things that I really liked that you mentioned about like Interstellar was that they used something called wormholes, where wormholes are like these shortcuts through space-time. They're my favorite method of space travel, because you're not, so you, if our understanding of physics is correct, or at least this part is, if general relativity is correct, relativity in general is correct, so relativity, like general relativity and special relativity, then we can't move, then nothing can move faster than light, and we can never even move as fast as light because we're massive, whereas photons are particles that are massless, so they can move at that speed. So wormholes being shortcuts through space-time, so like let's say there's like this, it's like a tunnel, like if you were to maybe take like, say, imagine space-time was like a paper, right? If it was just, it's like a fabric. We can't really picture in 3D, but if it was, and then, say like we're over here, and then we want to move to some point over here, then we kind of like, there's this tunnel here, which is like a wormhole where you can move right through and then bypass all that distance in between. So you're not really moving through space-time faster than light.
You're bending the fabric of space-time.
Right. And so
is that possible? Is that theoretically possible?
They actually do come out of Einstein's equations, wormholes. So theoretically they're possible, but the problem is traversable wormholes, so ones that we could actually use for travel, are unstable. So they would like collapse. And in order to hold these open, we would need a type of matter that has like, it's like a negative mass. That has negative mass, which doesn't make sense. And so we're still kind of left at this point where we're kind of stuck in the solar system at this rate.
Do you spend much time thinking about the future and fantasizing about living on other worlds, and where do you? I'm really interested to hear, like, let's not say 1,000,000 years, because then things will just get silly, but say 1,000 years in the future. We probably got some presence on the moon, Mars, moons of Jupiter. What else? What else should we be thinking this is going to happen in 10 generations, do you think?
I think about this stuff all the time because we have a couple of ways to actually to get out of the solar system. And so let me first, before I jump to that, let me first answer the first question. Within like 1,000 years, I guess it depends on what where physics goes. It's a very long time. We could discover many things along the way, and if we discover new physics, then that can lead to definitely new technology and new discoveries. And so in 1,000 years, I'm hoping that we can get out of the solar system, but at the very least, I think that humanity, because assuming that we don't, that we do survive and like we're able to keep this planet habitable for our longevity, eventually the sun is going to die. And so once that happens, the sun's going to die in like 5 to 10 billion years. So it's not even about waiting that long. In about a billion years, the sun's already going to expand and become too hot or Earth is going to become too hot for to host life. And so one thing that I see maybe is that we will start to, maybe we'll, be able to like inhabit planets like Mars. And at that point, we want to be able to live on, say, one of the moons of Saturn, like Titan. Because after that, we got to get out of the solar system, and there's no technology that we have that can do that. Like with our fastest spacecraft right now, the closest star system to us is Alpha Centauri, and it doesn't even have habitable planets, but that's the closest star system to us. It's about 4 light years away from us, and so that would take like 20,000 years to get there. And so, okay, if we figured out cryogenic freezing, then maybe we could do that and, freeze a bunch of bodies, go 20,000 years, and then, hope that we survive that trip, I guess. But, like, without big technological advances, like maybe using relativity to our advantage. So when you travel closer to the speed of light, then time moves slower for you relative to Earth, and distances become shorter. It's just the way that special relativity works. It actually happens. And so like utilizing those things, or perhaps finding wormholes, then we're kind of stuck in this solar system. And it's a little bit grim for me because I want us to become an interstellar species, but I don't see that happening in the next few hundred years. Maybe 1,000, I'm not sure. Or maybe never. I don't really know. I think it would require new physics, though. So I know this is a really winded
maybe
answer,
maybe there's someone listening to the podcast that will have an idea that will change the world. You never know. So what's your personal plans? So you finish your PhD. Sounds very shortly. Would you want to? How does it work in academia? Would you want sort of get tenure and stay at a university, continue? Studying your subject matter, and and
Yeah,
go down
so
that road?
uh-huh. So I guess it depends. Like in academia, at least in physics, if you wanted to stay in academia, so if you wanted to go on to being a professor and whatnot, you would go and do like a postdoctoral. You'd get a postdoctoral position at a university where you just do research, and then you would eventually hope that you could get a position as a professor, or you can go into industry. So like you can take your skills, which if you've done physics, then you're gonna become, you know how to code, because you can't do physics without coding. It's just it's in everything. Like you just can't. And so you get these sort of skills that you can use in different areas of life. Or you can work at a place like, where you could actually do this kind of research, like say NASA. And my dream would be to work at NASA. I would love to work at NASA and maybe guide some of the missions that are, done there, like for example, like what the James Webb Space Telescope might look at next, or whatnot. And there's that. There's also academia. I might stay in academia. I would definitely rather work at NASA, but there's some nice things about academia in that I get to I would get to teach, and I like to teach a lot. But the one thing that I know, that regardless of what I do, I'll always be doing science communication. No matter where I end up, science communication is going to be a part of my life, because I really love to talk about this stuff. So then I can go and take my wild imagination about how we're going to become an interstellar species, or if we ever will, and talk about that with people. And so yeah, that's kind of where I see myself, either at NASA, hopefully at NASA, perhaps, in continuing with academia, or maybe like another observatory or something, or a lab. But always I will be doing science communication. That's for sure.
You're brilliant at it. I mean, I appreciate you answering my very basic questions, and I'm not doing it for the audience. I'm doing it just for me, because I love thinking about it. And in everyday life, you don't really. You look up at the stars, and you have a moment every now and again, but you don't really think like, are we alone in the universe? Where did we come from? Will the Earth be here in a million years' time? You don't think about those things. So yeah, I think we need to share your message of getting people to think about the cosmos. Just before you go, there's some young physicists and scientists listening to this who are curious about the universe, and might be looking to study physics and science. What areas of interest would you recommend them looking at? Say they're not going to do dark matter, but what corners of the universe do you think should be looked at? Like if you could clone yourself basically and do take a deep dive into other subjects, what else is there that you would recommend? Look into that. That would be interesting.
Because physics is a very broad field. There's the cosmology or astrophysics is one part of it, but there's also like condensed matter physics. Where you actually work on like perhaps like making even like computer things for computers and stuff like this. There's solid state in there, and it's just there's plasma physics also. And so what I would recommend, if somebody took an interest in any of those sort of directions, or even just wanted to learn about whether what they're interested in, is I would always recommend, if there's an astronomy club around you, just join it, because even if it doesn't, even if that's not what you end up wanting to do, you're going to learn a lot of new things. You're going to meet a lot of really cool people and learn about the sky. And it's just amazing. That's actually one of the reasons why I ended up here, is an astronomy club in my undergrad institution. And going to like local science centers, and talking to your science teachers in school. Definitely speak to them about it, and read books, read a lot of books. There are really good popular science books out there that talk about like just break this stuff down in a really digestible way. I would say definitely do that. And since since we're kind of in the era of social media, follow people who do this stuff. Follow people who do science communication, and perhaps you will learn something that, that where, that kind of like, I guess, inspires you to try to go in that direction. And so that's I guess my biggest piece of advice is to, yeah, try to surround yourself with it. And because we're in the era of social media, it's not difficult to do.
100%. Sophia, thank you so much for coming on.
Thank you for having me.